Hello and welcome to the continuing saga of engineering fluid mechanics. And this next video is going to be an application of the concepts of drag in an unusual setting, but appropriate. Imagine, if you will, we have a bridge pier sitting in a rectangular channel, something like this. Here's our channel. Took a perfectly good angle and we broke it, hence it's called a rectangle. That was a pun. For those of you that didn't get it, well, that's just too bad. So this center pillar is the obstruction to flow, the bridge pier. And we'll go ahead and get the dimensions in. 2 feet across, total channel width is 8 feet. Discharge will be 240 cubic feet per second. And the normal depth in the channel far downstream is 5 feet. So that's the information we have. There's the end view. Here's our elevation view. Here's the bridge pier. And we'll go ahead and introduce our water surface into the system. So here's the water flowing around the bridge pier. Its depth is unknown. And as the water approaches the bridge pier, it piles up. Leading edge accelerates going around it. Comes back up, and at some distance away, we're at y subnormal. On the downstream end, we have Q equals 240 feet cubed per second, and our desire is to find out y sub 0 at the upstream end. Well, let's go ahead and apply our usual analytical techniques. We'll go ahead and we'll draw a control volume. So there's my control volume. So when I extract it out, I have this diagram, and we want to go ahead and apply the forces. There's some frictional shear from the water contacting the sides and the bottom. There is a drag force induced by the pier that pushes on the water. There's the assumed hydrostatic pressure distribution on this end, which produces a force FP. We'll give that a notation. We'll call that FP2. Hydrostatic pressure distribution on this end produces a force FP1. We'll name our sections Section 1, Section 2, and we also have whatever the velocity of 1 is, area 1, velocity 2, area 2, and there is the weight force of the water. These should be red because they're forces also. All right, so there is our setup. Now, let's see how we can proceed with that. If we use table 11.1, we can look up a drag coefficient for a cylinder is 2.0. Let's go ahead and verify that that is actually true. Plus the escapist, we find lecture 11, and it's 11.1. It's the table that we want. Where is my table? There we go. My bridge pier is a square rod, drag coefficient of 2. The other way to do it would be to use the flat plate. Now, whether you want to use a square bridge pier or circular one would probably be more common in actual practice, but we'll pretend it's a rectangular bridge pier. Everything else is rectangular. So that's our drag coefficient. Well, let's write our drag force. We know that the drag force, depicted right here, of the pier on the water is equal to 2.0 times 2 y sub 0 times rho v1 squared over 2. That's direct application of the definition of drag force. The upstream pressure is rho g times the width of flow times y0 squared divided by 2. So that's this pressure distribution. The downstream pressure distribution is rho g times the width of flow, happens to be 8 in this case. Y2, I'm calling it yn squared over 2. Okay, the one remaining force is the frictional shear, and we'll just acknowledge that it exists. We don't have a value for it yet. In fact, we're actually going to assume it away. Let's now recall our momentum balance. So the sum of the forces in the x direction is equal to pressure force at 1 minus pressure force at 2 minus the drag force minus the frictional shear. And so this is equal to rho g w y0 squared over 2 minus rho g w yn squared over 2. The drag force evaluates as 4 y 0 rho v1 squared over 2. And the frictional shear we will assume negligible. And that's equal to the change in momentum, which is rho v2 q minus rho v1 q. So this is the integral of the control surface of rho v v dot dA. We now can attempt to populate it. Our unknown is y0. W is equal to 8 feet. Every term has a row in it, so it looks like we can cancel that. Row, 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 row your boat gently down the stream. The 4 about here in the projected area, the drag force, as you recall, is C sub d times the area, rho v1 squared over 2. The area is the area of the pylon. So that's the 2 feet times the y0. So that's where that's coming from. So let's now see what we can do to express the velocities. Velocity at section 1 is equal to q over the width times y0. The velocity at section 2 is equal to q over the width times y sub n. Y sub n is known. So our resulting term is g w y0 squared over 2 minus g w yn squared over 2 minus 4 y0 over 2 q over w y0 quantity squared equals q squared over w y n minus q squared over w y0. Only unknown is y0. Probably the easiest thing now is to just make a table. So we'll guess a value for y0. From that, we'll compute the various pieces of the equation. Basically, we'll compute the left-hand side based on y0, the right-hand side. So y0 produces a left-hand side, y0 produces a right-hand side. We take the left-hand side minus the right-hand side. So we have a table that looks like that. And in this column, we're looking for a 0. All right, so this is kind of a pain in the neck to do by hand on a calculator, but it should be a little bit simpler doing it in our scripting language. Okay, save that, disappear it. Let me clear my console. Ta-ta for now. New script. And we will script in a left-hand side function and a right-hand side function. The left-hand side is a function And what does it depend on? It depends on gravity, width, discharge, y0, y1. I think that's all we need. And we start building the parts of it. Just use a bunch of temporary variables. Gravity times width times y1 quantity squared. That whole thing is divided by 2. Okay, so that's temp 1. Oh, let's be more from term 1. Build the second one, term 2 is the same thing. That's y0 with respect to y1. Term 3 is equal to, I probably should do it as c sub d, but I didn't. 4 over 2 is 2. Two times y0 times discharge divided by width times y0. Get everything grouped properly. That whole thing is squared. And left-hand side is equal to term 1 minus term 2 minus term 3. Return left-hand side. Right-hand side, function of width, discharge, basically function of all the same things. Cool thing about a function, you don't actually necessarily have to use an input variable, a particular input variable. So this is equal to discharge squared divided by width times y1 discharge squared divided by width times y0. Term 1. And let's get these grouped so it'll guarantee that the exponentiation occurs before the division. It's not supposed to screw up, but it is a computer and that's what they're built to do. See, it even made me spell it wrong. Alright, right hand side is term 1 minus term 2. Okay, the comparison produces is compare is right hand side minus the left hand side. Not very exciting. All right, let's save this as bridge pier. Hit the Save, source it. Actually, let's clear the workspace. Good. All right, so now everything's loaded in, and so all we have to do is a compare. And we have to provide gravity, which is 32.2. We have to provide a width, which in our case was 8. We have to provide a discharge, which in our problem was 240 feet per second. We have to provide the y0, which we don't know what it is, but let's start at 5. y1 equals 5. And we get a value of 360. And so that means that our approach depth is not correct. Let's see what happens when we make it bigger. We get a value of minus 876. So what that means is that the correct approach depth is between 5 and 6 feet. Let's split the difference. We need to make it a little bit smaller. So it's between 5 and 5.5 feet. We'll split the difference again. Okay, it's between 5 1/4 and 5.5 feet. 1, 2, let's go to 37. Okay, it's between 5 1/4 and 5.37. Let's go to 5.3. It's between 5.3 and 5.37. It's between 5.3 and 5.32. 5.3195 and 5.32. Yeah, that's good enough. 5.31968. Let's call it 5.32. And so now we have the correct approach depth, which is 5.32. Let me go ahead and list the results here. So we made our first guess of 5. We got 360. We went to 6. We got a minus 876. Went to 5 1/4. We got to 81.37. We made a whole bunch of guesses. 5.32. We have a minus 0.386, and we're going to call this one close enough. And that was the result of the bridge pier analysis. Again, the trick here is we do analysis as far as necessary, and then there's no shame whatsoever in using numerical techniques or calculator techniques to search for the correct value that makes the difference between the left-hand side and right-hand side vanish. And we could get this quite a bit closer to 0, but we would be specifying values of depth that are, under current technology, unmeasurable. The difference between 5.32 feet and 5.3199689, well, arithmetic-wise is a difference. We don't have tools that can measure changes in water depth that small. In fact, if a moth were to fart in that river, that would cause enough of a wave that we couldn't tell the difference between moth fart and actual 0. All right, that concludes this video, and the brief introduction to forces of drag and forces of lift.